In this video, I'll discuss commutability of rotation and reflection. Suppose we have two operators, two symmetry operators R1 and R2. If we have some object here with a given configuration, and if we apply R1 on it, we'll get a new configuration. Then again, if we apply R2 on the result, we'll get another configuration. We can do it in the reverse order. We start from the original configuration, first apply R2, and then on the result we can apply R1. If we find that this result and this result are the same, then we say that these two operators commute. We'll study such commutation property for a rotation and reflection operator. Let us start with our familiar example of water. This is the original configuration of H2O molecule. This is a C2 axis, and there are two reflection planes. One is a plane like this, symmetry plane like this, cutting the object into two equal halves. This is sigma, and the molecular plane itself is another symmetry plane, which is called sigma primed. Now, if we carry out a C2 operation first, we'll get a configuration like this. H1 comes here, and we need a bar notation because by rotation the front side goes to the back side. Here H becomes 3 bar, and here oxygen becomes 2 bar. Now on this configuration we apply the reflection operator on this plane using this plane of symmetry. Reflection operator. What do we get? These two will change their positions. Oxygen will remain in its own place. H3 bar comes here, and H1 bar, 1 bar goes there. This is the resulting configuration of these two operations carried out successively. And how can we come from this to this? By a single symmetry operation, by sigma primed, because if we reflect on this plane, the atoms will remain in their own positions, but the associated atomic orbital lobes or vectors will be inverted by this reflection. So H1 becomes H1 bar, H3 becomes H3 bar. Thus, sigma primed operation will give this result from this. Therefore, we can write C2 operation followed by sigma operation. C2 followed by, this order is to be maintained. The first one is written on the right hand side, the next one is written on the left. This result is sigma primed operation. Now let us do it in the reverse order. First we carry out sigma operation, reflection on this plane, we get H3, H1, O2, and then we carry out a C2 rotation. C2 means this rotation. Then 1 will become 1 bar and go to this place. 3 will become 3 bar and go to this place. So by a C2 rotation we get this. Therefore, Therefore, first sigma, then C2 will also be sigma primed. This way or that way, the result is the same. Therefore, C2 and sigma primed commute. C2 and sigma commute. Next, let us consider our second familiar example, ammonia. Ammonia molecule. It has a C3 axis like this, C3, and each NH bond together with the C3 axis will give a plane of symmetry. This is a plane of symmetry which contains the NH bond and the C3 axis. Similarly, this again is a plane of symmetry and containing the C3 axis and this NH bond, there is another plane of symmetry. There are three sigma planes. If we label the atoms as 1, 2, and 3, the reflection planes will be labeled as sigma 1, sigma 2, sigma 3. To simplify the diagram, we take the base atoms, hydrogen atoms, 1, 2, and 3. We denote the reflection planes in this manner. Sigma 1 is this plane, sigma 2 is this plane, and sigma 3, all are vertical planes. Sigma 3 is this plane. All the planes are perpendicular to the plane of the paper, and the C3 axis is here. It is perpendicular to the plane of the paper and passes through the center of the triangle. Nitrogen atom is somewhere above the plane of the paper. Now we carry out a C3 rotation first about this axis. Then 1 comes here, 2 goes here. We get a configuration like this. 1 here, 2 here, 3 here. The reflection planes, however, do not move. This is to be remembered very particularly, that when the atoms move to equivalent positions by a symmetry operation, the symmetry elements, that is symmetry planes or symmetry axes, do not move. Therefore, after this rotation, the sigma 1 plane remains here. Sigma 1 plane is still here. This is the sigma 1 plane. Therefore, if we carry out, if you move the plane, if you think that since atom 1 has moved here, sigma 1 plane also has moved here, then, and if you draw a sigma 1 plane in this manner, then you will get into confusing result. Remember that the symmetry elements do not move when symmetry operation is carried out. Therefore, this is the configuration after C3, and then we carry out sigma 1 operation. What will happen? These two will exchange positions. So we will get 3, 2, 1. And how can we come from this to this? By a single operation. 2 is in its own position. 1 and 3 have exchanged places. Therefore, this is a simply sigma 2 operation. So we can write C3 operation first, then sigma 1 is equal to sigma 2. Now do it in the reverse way, reverse order. First sigma 1, what will happen? We'll get this, 1 will remain here, 3 comes here and 2 comes here. Now C3 rotation about this axis, we get 1 here, 3 here, and 2 here. And how can we come to this configuration directly from the original one? We see that 3 is in its own position, 3 here and here. The atom 3 has not moved. 1 and 2 have exchanged places. Therefore, this is a sigma 3 operation. So we can write here sigma 1 first followed by C3 is equal to sigma 3. The results are different. Therefore, C3 and sigma 1 do not commute. And we also note that the rotation axis is contained by the reflection plane. The reflection plane contains the symmetry axis in both cases. Here, the C2 axis is contained by sigma 1. You can draw the C2 axis on this sigma 1 plane. You can draw the C3 axis on the sigma 1 plane. Here also, C3 axis on the sigma 1 plane. So when a reflection plane contains an axis of rotation, the rotation and reflection operations may or may not commute. In some cases they commute, in some other cases they do not. We shall now examine what happens if the reflection plane is perpendicular to, if the reflection plane Cn, reflection plane sigma is perpendicular to the rotation axis Cn. What happens then? To see this, we take the case of BF3. It has a C3 axis passing through boron atom and perpendicular to the plane of the paper, a C3 axis. This is a C2 axis. Every BF bond is a C2 axis. There are 3 C2 axes. This is also a C2 axis. And the plane of the molecule is a plane which is perpendicular to the C3 axis. We call it sigma perpendicular. There are other symmetry planes also, but we are considering here the plane of the molecule as a plane of symmetry. That plane is denoted by this symbol to indicate that it is perpendicular to the C3 axis. Now, label these atoms as 1, 2, and 3. If we carry out a C3 rotation first, C3 is an axis like this, perpendicular to the plane of the paper. And 1, 2, and 3, this will give a configuration like this. 1 will come here, 1, 2 comes here, 3 goes there. No bar notation is needed, clearly. And then we reflect on this plane. What will be the resulting configuration? Resulting configuration will be 3 bar, 1 bar, 2 bar. And do it in the reverse order. Sigma perpendicular operation first, then you get this configuration, 1 bar, 2 bar, 3 bar, and then carry out a C3 rotation. You will get 1 bar here, 2 bar here, and 3 bar here. These two are not the same. They are not the same. Therefore, no, they are the same. These two are the same. Therefore, C3 operation followed by sigma perpendicular operation is equal to sigma perpendicular operation followed by C3. So commutation is achieved. the two operators commute, C3 operator and sigma perpendicular operator commute. This is the case always. Whenever a CN axis is perpendicular to a reflection plane, the operator Cn and sigma perpendicular always commute. And therefore, the composite operation Cn sigma perpendicular or the reverse of it is a single symmetry operation. You can come from this to this by no other means. You have to follow this path. This direct path should be written as a combined operation of sigma perpendicular C3. By a composite operation like this, you can come from here to here. No other operation derived from these elements or this element separately, this reflection plane or this rotation axis individually cannot cause this transformation from this one to this one. This is entirely a new operation, and we call this operation an improper rotation of order 3, or improper threefold rotation. Order is something else. I will discuss that later. This is a threefold improper. This threefold proper axis of symmetry also behaves like a threefold improper axis of symmetry, and such an operation, either this or this, is an improper rotation. Rotation followed by reflection, or reflection followed by rotation, the plane of reflection being perpendicular to the axis of rotation. This is denoted by Sn. The general operation is denoted by an Sn operation. It is called an improper rotation. The commutability of Cn and sigma perpendicular allows us to define this operation. If the results were different by reversing the sequence of these two, then this could not be defined as a single symmetry operation. Because of commutation of Cn and sigma perpendicular, we can define Sn. I will discuss more elaborately about improper rotation in a next video. So let me thank you for watching.